Massive stone structures stand as silent monuments to an ancient mystery. How did civilizations without advanced tools carve and move granite with such perfect precision? The answer lies in forgotten material science innovations that rival modern engineering. By the end of this video, you will understand the real methods that allowed ancient builders to master hard stone. We will uncover how sand became a cutting tool and why some stones might have been softened like clay. These secrets challenge everything we thought we knew about the past. What does this lost knowledge reveal about human ingenuity? The workshop of an ancient stonemason was a world of unyielding resistance. Every surface was dominated by materials like granite, quartzite, and basalt, stones so hard they could easily dull or shatter a modern steel blade. These were not the soft limestones or sandstones a beginner might practice on. These were the geological titans, chosen for their defiance against time itself. Their immense durability made them perfect for monuments meant to last for eternity, and their sheer presence conveyed power and permanence. Yet, this choice created a profound technological puzzle. How do you shape a material that is harder than nearly every tool you possess? A copper chisel, the strongest metal commonly available for much of antiquity, would be rendered useless after just a few strikes against a block of granite, its edge folding over like soft clay. Archaeologists like Dunn Stocks have calculated the staggering labor involved, where simply carving a few hieroglyphs into a granite slab could require weeks of painstaking effort and countless destroyed tools. This was not a matter of brute force. The persistent, almost stubborn selection of these impossible stones across different cultures, from the obelisks of Egypt to the statues of Easter Island, signals something far deeper than convenience. It points to a deliberate pursuit of a technical ideal. The challenge of the material itself appears to have been the very catalyst for innovation, pushing ancient engineers to discover solutions that bypass the problem of hardness entirely. Why struggle with a substance that laughs at your strongest tools? The answer lies not in overpowering the stone, but in outthinking it. The solution emerged not from a new tool, but from the ground beneath their feet. An Egyptian artisan would have dragged a simple copper saw back and forth across a granite block, a seemingly futile exercise, but then a handful of wet quartz sand was sprinkled into the cut. Instantly, the soft metal blade was no longer the cutter, it was merely the carrier. The real work was done by the countless microscopic quartz crystals in the sand, each one harder than the granite itself. This simple slurry created a grinding paste that transformed a soft metal tool into an effective stone cutting machine. The innovation was profound, a fundamental shift in thinking. It was not about making a harder tool, but about using the tool to deploy a harder substance. The copper saw became a delivery system for millions of tiny, durable cutting teeth, each one scraping away a minuscule amount of stone with every pass. This method allowed for astonishing control, enabling artisans to slice through massive granite blocks with patient, steady effort, or to carve intricate hieroglyphs with delicate precision. Historical evidence and modern experiments confirm this was a standard practice. Workshops would have had piles of specific sands gathered for their abrasive qualities, a curated material supply for industrial-scale stoneworking. This clever understanding of comparative hardness, using a naturally abundant resource to solve an impossible problem, is a cornerstone of ancient engineering. It demonstrates that their greatest tool was not copper or bronze, but a deep, observant knowledge of the material world around them. But that same understanding of abrasives unlocked an even more precise technology. Picture a hollow copper tube, perhaps no wider than your thumb, being pressed against a granite block. The tube itself is soft, but it is packed with a wet, gritty slurry of quartz sand and water. As a craftsman rotates this tube back and forth with a simple bow, something remarkable happens. The abrasive paste trapped under the tube's rim begins to grind a perfect circular groove into the impossibly hard stone. This was the birth of tube drilling, a method that seems to defy logic. The hollow core was its secret genius. Unlike a solid drill bit that would have to grind away the entire volume of stone, the tube only had to cut a narrow ring, saving an immense amount of labor and material. The central core of stone could simply be broken free and removed, leaving a clean, cylindrical void behind. Modern engineers like Christopher Dunn have recreated these drills and found they work with startling efficiency. The recovered core samples themselves tell the story, often marked with delicate, spiral grooves that are the unmistakable signature of a consistent, rotational cutting motion. This was not crude pounding, it was a controlled, mechanical process. The evidence is etched into history, visible in artifacts like the exquisitely drilled granite boxes found at the Serapeum of Saqqara in Egypt. Their surfaces feature holes and cavities with such sharp, precise edges and consistent depths that they suggest a process that was not just possible, but repeatable and mastered. This innovation transformed construction. It allowed for complex stone joinery, where massive blocks could be locked together with stone dowels fitted into these drilled holes, creating structures of immense stability. What level of intuitive physics was required to conceive of this? They had to understand rotational force, the distribution of pressure, and the behavior of a liquid abrasive under friction. This was not random experimentation, it was applied material science. The mastery of rotary drilling did not just make holes, it opened the door to an entirely new level of architectural ambition. Granite, for all its stubborn permanence, holds a secret weakness. Deep within its crystalline structure, different minerals expand at different rates when heated. Ancient builders learned to exploit this fundamental flaw with a method as primal as it was brilliant: fire setting. They would light controlled fires directly against a granite cliff face, allowing the flames to wash over the stone for hours. The intense heat would cause the individual crystals to push against each other, building up immense internal stress. Then, at the critical moment, workers would douse the scorching rock with water. The resulting thermal shock was devastating. The rapid, uneven cooling caused the stressed stone to fracture and spall, creating a network of cracks that ran deep into the bedrock. This was not about melting the stone, but about convincing it to break itself apart from the inside. From the tin mines of Cornwall to the great quarries of Central America, this technique allowed workers to isolate colossal blocks that would have been utterly immovable by mechanical force alone. The evidence is still visible today on ancient quarry walls, marked with layers of soot and a distinct reddish discoloration from the intense heat. This pyrotechnic approach reveals a sophisticated, pragmatic understanding of thermodynamics. They were not just using fire, they were using it as a precise, albeit risky, geological tool. How did they learn to gauge the perfect amount of heat to weaken the stone without reducing it to rubble? It speaks to generations of accumulated observation, a slow-motion science born from watching stone itself react to the elements. This knowledge turned an insurmountable obstacle into a manageable process, allowing them to harvest the very bones of the earth. Yet for all its power, fire setting was a method of brute fracture. What happened when the task required not just breaking stone apart, but giving it a perfectly smooth, almost liquid-like finish? But the most enigmatic whispers from the past suggest a method that seems to border on magic. Legends from across the world speak of a lost art, a way to make the stone itself surrender its hardness. The stories describe plant juices and herbal extracts, carefully prepared and applied to a granite surface. After a time, the stone would reportedly become temporarily soft, almost like clay, allowing artisans to mold and carve it with incredible ease before it reset to its original, diamond-like state. This sounds like pure mythology, yet the idea is too persistent to dismiss entirely. If true, this would represent the pinnacle of ancient material science, a form of early chemical engineering that manipulated stone at a molecular level. Researchers have explored the plausibility of this, noting that certain plants, like sorrel, contain high levels of oxalic acid. In laboratory settings, such organic acids have been shown to subtly etch and weaken the silicate bonds that give granite its strength, effectively reducing its surface hardness. This is not about melting the rock, but about chemically convincing it to become more pliable. Early accounts from explorers and indigenous traditions often mention these techniques in passing, treating them not as legend, but as a lost practical knowledge. The innovation here would be a profound shift in perspective. It suggests that ancient builders did not see stone as an inert obstacle to be conquered by force alone. Instead, they may have viewed it as a material that could be negotiated with, its very properties altered through a deep botanical wisdom. What level of environmental observation would it have taken to identify which specific plant, among thousands, possessed this unique reactive property? The preparation of such a solution would have been a form of alchemy, a secret recipe passed down through generations of master craftsmen. While direct archaeological evidence for this practice remains elusive, its theoretical possibility forces us to reconsider the entire mechanical paradigm. Perhaps the true innovation was a holistic one, combining the brute force of thermal shock with the delicate precision of abrasives and the subtle influence of chemistry. This trio of methods working in concert could explain the otherwise impossible feats of stonework that still leave us in awe today. The granite block must have seemed like a perfect, unbroken entity. Yet the ancient stonecutter knew its hidden fault lines, the invisible paths of least resistance running through its crystalline heart. Their method for revealing these paths was a masterpiece of applied physics. They would drill a series of perfectly aligned holes along the line where they wanted the stone to split. Into each hole, they placed a pair of curved metal shims, the feathers, and between them, a narrow wooden wedge. The initial taps of the hammer set the stage, but the true force came from a simple, natural agent, water. As the dry wooden wedges were soaked, they began to swell, their expansion confined by the unyielding metal feathers. Within the heart of the granite, an immense isotropic pressure built up, a force pushing outward in all directions equally. This pressure did not crush the stone, it coaxed it, convincing the rock to separate along its own natural cleavage plane with a sharp, clean crack. This was the wedge and feather technique, and its genius was in its control. Unlike the chaotic fracture of fire setting, this method allowed artisans to predict exactly where a multi-ton block would split, minimizing waste and producing perfectly flat faces ready for construction. The precision of the final split was not left to chance, it was a direct result of calculation. How did they determine the exact spacing and depth for those critical holes? It was a knowledge born from generations of observation, a deep empirical understanding of how different types of stone would fail under stress. A mistake in placement could shatter the entire block, turning a valuable resource into rubble. This mechanical intelligence was applied across the globe, from the quarries that supplied stone for India's elaborate temples to the volcanic slopes of Easter Island, where it was used to separate the iconic Moai statues from the bedrock. The principle is so fundamental that it is still used in quarries today, a direct technological thread connecting us to those ancient engineers. They had mastered the art of persuading stone to break itself, not with random blows, but with a patient, escalating force that turned the material's own internal structure into an ally. This was not brute force, it was a conversation with the stone, a dialogue of pressure and fracture that yielded perfectly shaped building blocks from the most stubborn of materials. The rhythmic sound of stone striking stone would have echoed through the quarries and building sites, a percussive heartbeat of ancient industry. Teams of workers, each wielding a heavy, fist-sized hammer of dolerite, would methodically pound the surface of a granite block. Dolerite is a stone even harder than granite, and this was the key. With every impact, the dolerite pounder would pulverize a tiny, microscopic grain of the granite surface, turning it to dust. It was a process of relentless, patient abrasion through pure percussion. This was not a chaotic beating, but a controlled, rhythmic application of force, gradually convincing the unyielding stone to surrender its shape. The innovation was in the material choice itself. By selecting dolerite, a stone that could withstand thousands of impacts without shattering, ancient builders created a durable, reusable tool. They turned brute force into a predictable manufacturing process, a form of mechanical grinding on a monumental scale. Thousands of these stone pounders have been found at sites like the Great Pyramid Complex at Giza, their worn, rounded surfaces telling a silent story of immense, sustained labor. This method was essential for creating the perfectly flat surfaces and subtle curves we see on megalithic foundations from Peru to Japan. Achieving such precision across a vast stone face required more than just strong arms. It demanded incredible coordination. How did they organize large groups to ensure every strike contributed to a unified, level plane? It suggests a system of overseers and markers, a shared understanding of the final form that guided every rhythmic blow. The widespread reliance on this stone-on-stone technique reveals a universal, pragmatic solution to the central problem of hardness. It was a technology of pure persistence, proving that with the right natural tool and unwavering determination, even the toughest stone could be mastered. The final touch on a granite statue was not a matter of brute force, but of delicate chemistry. After the pounding, sawing, and drilling were complete, the surface would have been a cloudy, scratched landscape, bearing the marks of every tool used in its creation. To erase this history and reveal the stone's hidden soul, artisans turned to a sophisticated final act, the art of the perfect polish. They created specialized pastes by mixing fine powders of exceptionally hard minerals like emery or corundum with water or oils. This was the birth of the composite abrasive, a material innovation as crucial as any tool. The paste itself was the technology, a carefully calibrated suspension of cutting particles in a smooth carrier. The oil did more than just hold the powder together. It acted as a lubricant and coolant, preventing the fine abrasive from loading up with stone dust and ensuring every microscopic crystal could make a clean, sharp cut. The process was a study in patience and progression. A worker would begin with a slightly coarser grit to remove the deepest scratches, then move through progressively finer and finer powders. Each grade of abrasive erased the marks left by the previous one, refining the surface down to a microscopic level of smoothness. The final result was a mirror-like finish that seemed to capture light within the stone itself, a luster so deep it appeared liquid. Artifacts like the polished granite sarcophagi from ancient Egypt bear witness to this mastery, their surfaces so flawless they reflect like dark water even after thousands of years. This was not a simple rub with sand, it was a controlled, multi-stage industrial process. How did they store these valuable polishing compounds, and how were they applied over the many days or weeks a single statue might require? The creation and use of these pastes point to a specialized knowledge of viscosity and tribology, the science of friction, wear, and lubrication. The pursuit of this perfect polish reveals something profound about these ancient builders. Their innovation was driven not just by practical necessity, but by a powerful aesthetic vision. They understood that to truly complete the stone, to make it live and breathe, they had to give it light. This was the moment when inert rock was transformed into a testament of human artistry, a fusion of material science and beauty that continues to captivate us today. Before a single tool ever touched the stone, the true work had already begun. Ancient builders were the original material scientists, walking the landscape with an expert eye not just for shape, but for substance. They understood that every block of granite or limestone had a hidden personality, a unique internal world defined by the size, shape, and alignment of its crystals. This was not random selection, it was a strategic science. By choosing stones with a consistent, fine-grained crystalline structure, they were selecting a material that would fracture more predictably and polish more smoothly. A granite with large, interlocking crystals of feldspar and quartz might look impressive, but it could be a nightmare to work, fracturing unpredictably along the boundaries between those different minerals. But a granite with a uniform, smaller grain size offered less resistance, behaving more like a homogeneous mass that could be split and shaped with greater control. This deep knowledge of petrology, the study of rocks, was their first and most crucial innovation. It was all about reducing the inherent difficulty of the material before the labor even started. Why would a civilization transport specific types of limestone over hundreds of miles when a local, seemingly identical stone was available? The answer often lies in the details invisible to the untrained eye. The preferred stone might have had fewer hard flint nodules, those stubborn, dark lumps that could shatter a chisel and ruin a perfect surface. Transporting that ideal stone across vast distances was not an act of folly. It was a calculated investment in quality and efficiency. This implies a sophisticated, though unwritten, classification system for rock properties. What simple field tests did these ancient geologists perform at the quarry face? They might have struck a candidate stone with a hammerstone, listening to the ring it produced, a clear tone indicating a sound, solid piece, while a dull thud might suggest internal flaws or cracks. They would examine the surface for telltale signs of weathering or inconsistent coloring. They might even have made a test cut with an abrasive saw to see how the stone responded. This empirical knowledge, passed down through generations, was the invisible foundation upon which every monumental structure was built. The choice of stone was the first and most important cut, a decision that set the stage for all the shaping, drilling, and polishing to come. It was an innovation of the mind, proving that their greatest strength was not in their muscles, but in their meticulous, observant understanding of the very earth they sought to master. The silence of the quarries may have been broken by more than just the sound of hammerstones. A more elusive idea whispers from the edges of history, the possibility that ancient artisans learned to shape stone not just with physical tools, but with the invisible force of sound itself. Oral traditions from diverse cultures speak of technologies where specific chants, drumming, or the sustained tones from massive horns could, in some accounts, make colossal stones lose their weight or become easier to work. This is the speculative frontier of sonic or vibrational resonance. The theoretical principle is one of matching frequencies. Every object, including a massive granite block, has a natural resonant frequency, a specific pitch at which it vibrates most easily. The innovation would be the deliberate application of a matching sound wave, a constant, powerful hum that travels through the stone. This wouldn't melt the rock, but could set up a sympathetic vibration within its crystalline structure, creating microscopic internal stresses that fatigue the material. Much like a repeated, gentle push can eventually cause a swing to move with great force. This internal agitation could, in theory, make the stone more amenable to fracturing along desired lines or easier to abrade with other tools. Some experimental archaeologists have tested these ideas with modern equipment, noting that certain frequencies can indeed affect the behavior of granular materials and stone. The challenge lies in the immense, sustained energy required to affect something as massive and dense as granite. What kind of instrument could generate such a powerful, focused wave? Could it have been a massive, skin-covered drum struck in rhythm by many people, or a long, ceremonial horn designed to produce a deeply penetrating monotone? While mainstream archaeology remains skeptical due to a lack of direct, verifiable evidence, the persistence of these accounts forces a fascinating question. Could this represent a lost branch of material science, one that viewed energy and vibration as tangible tools? It suggests an intuitive grasp of wave physics, an understanding that the world is not just solid matter, but a constant interplay of forces. If even partially true, this would mean the greatest innovation was not a tool you could hold, but a knowledge of how to make the very air become a chisel. The final, most delicate carvings on a granite surface might not have been cut at all, but gently persuaded. A faint, almost invisible line appears on the stone, the outline of a sacred symbol. Instead of a chisel, an artisan applies a paste made from crushed, fermented fruit or sharp vinegar, carefully contained within a shallow clay bowl. The mixture sits on the surface, a patient, chemical whisper against the stone's roar. This is the speculative art of acid etching, a method of surface modification that traded force for a slow, controlled reaction. The mild organic acid would not dissolve the granite, but it could selectively attack the bonds between the mineral crystals, particularly the feldspar, creating a microscopically weakened layer. After the paste was washed away, this softened skin could be worked with far less effort, allowing for the creation of incredibly fine lines and intricate details that a vibrating chisel might shatter. The innovation here was a form of early chemistry, an understanding that the surface properties of a material could be temporarily altered to suit a task. How would they have applied this with such precision? A simple brush made from animal hair or plant fibers could carry the solution, or a dam of beeswax might be used to contain it, preventing the acid from marring adjacent areas. While direct proof is challenging to find after millennia, some of the most elaborate hieroglyphs in hard stone display a crispness and depth that seems to defy the limitations of abrasive slurry alone. Experimental work has shown that even weak acids, given enough time, can etch a noticeable pattern into limestone and marble. For cultures that valued perfection in their sacred art, this chemical assistance would have been invaluable. It represents a different kind of intelligence, one that sought not to conquer the stone through impact, but to collaborate with it through a subtle molecular dialogue. What other natural substances did they test, and what was the trial and error that led to this precise recipe? This potential technique suggests their toolkit was as much about botany and chemistry as it was about physics and force. A single wooden beam placed under the edge of a 20-ton stone becomes the most powerful tool on the construction site. The innovation of the lever is simple in concept, but its application by ancient engineers was a masterpiece of systematic genius. They did not just use a single lever, they orchestrated entire lifting ballets. For a task like raising an Egyptian obelisk base or positioning a Stonehenge lintel, teams would work in a coordinated rhythm. A series of levers, each with its own stone fulcrum, would be inserted along one side of the massive block. On command, each team would apply their weight, lifting the stone a mere finger's width. Before the wood could buckle under the strain, wooden cribbing was swiftly shoved into the newly created space. The levers were then reset, and the process repeated, lifting the colossal weight in a series of safe, incremental steps. This was not about sudden, heroic effort, but about patient, calculated escalation. The true brilliance lay in the multiplication of force. A team of 5 people, using a long enough lever and a sturdy fulcrum, could generate enough lifting force to raise a stone weighing many tons. By employing multiple leverage points simultaneously, they distributed the immense stress, preventing any single point of failure that could shatter the stone or the timber. How did they test these complex arrangements without the safety net of engineering manuals? Their testing ground was the quarry itself, where smaller-scale experiments with different woods, fulcrum shapes, and team coordination would have built an unshakable empirical knowledge. This mastery of mechanical advantage transformed the landscape. It allowed them to work with stone sizes that remain logistically challenging even today, proving that the greatest force multiplier was not raw power, but an intimate understanding of physics, patience, and precision. The relentless flow of a river carves canyons over millennia, but ancient engineers learned to harness that patient power in a single afternoon. They guided water itself to become a precision tool. Imagine a team directing a stream of water, thick with sharp quartz sand, through a sturdy leather tube held firmly against a granite block. This was not a wild flood, but a controlled, focused jet. The innovation was in the conduit, a simple channel that transformed a random flow into a directed cutting beam. The water acted as both a carrier and a force, pushing the abrasive particles with relentless pressure against the stone surface. Each tiny crystal in the slurry became a miniature chisel, and the flowing water ensured a constant supply of fresh, sharp grains, preventing the paste from becoming clogged and ineffective. This hydraulic force, combined with abrasives, allowed for the creation of long, smooth channels and graceful curves that would have been incredibly difficult to achieve with a handheld saw or drill. The method required a deep understanding of containment. How did they prevent the abrasive-laden water from eroding the surrounding areas, ruining the precise lines they sought to create? They likely used dams of clay or wax to outline the desired path, creating a shallow canal that confined the corrosive stream to its intended track. This technique represents a harmonious integration of natural forces into the manufacturing process, a collaboration with the element of water itself. It was a way to let the landscape do the work, reducing the physical strain on the worker while achieving a new level of fluid, organic form in the hardest stone. The presence of smoothly rounded, U-shaped channels in certain ancient structures, which lack the telltale marks of a chisel, whispers of this possible technique. While direct archaeological evidence for these temporary leather conduits is understandably rare, the principle is sound and aligns perfectly with the advanced hydraulic engineering we know these cultures possessed. They were not just fighting the stone, they were recruiting the very flow of water to help shape it. A profound shift occurred when ancient engineers stopped just shaping the earth and began to invent new stone from scratch. In workshops and mixing pits, they combined common materials like quicklime, volcanic ash, and crushed rock aggregates with water, creating a thick, workable paste. This slurry could be poured into wooden molds or used as a powerful mortar, hardening over time into a substance as durable as the hardest natural rock. This was the birth of synthetic stone, a material innovation that fundamentally changed the rules of construction. The chemistry involved was remarkably sophisticated. The process of calcination, burning limestone at high temperatures to produce reactive quicklime, required precise control. Then, through slaking and mixing, a chemical reaction called hydration would begin, forming interlocking crystals that bound the aggregate into a solid, monolithic mass. The Roman development of opus cementitium is the most famous example, a concrete so resilient it has withstood 2,000 years of seawater in harbors like Portus Cossanus. Yet evidence suggests even earlier civilizations, from the lime plasters of Çatalhöyük to the geopolymer-like binders in some Egyptian monuments, were experimenting with these principles. The innovation here was a complete paradigm shift. Instead of spending immense labor to quarry, transport, and carve a multi-ton block, builders could now create vast, seamless structures by casting a liquid stone that would set in place. This approach bypassed the entire problem of hardness, as the material was soft and malleable during its working phase. How did such a complex formula, requiring specific ratios of lime, pozzolanic ash, and aggregate, become standardized across a vast empire? It points to an established, almost industrial knowledge transfer, where the recipe for artificial stone was a valued technology disseminated by skilled artisans. The creation of these composite materials represents the ultimate expression of ancient material science, moving from mastery over nature to a partnership with it, synthesizing the very bedrock of their world. The quarry master's first task was not to cut but to listen. He would walk the rock face, his eyes tracing the subtle lines and color shifts in the granite, his hammerstone tapping lightly against the surface. Each tap returned a different sound, a clear ring indicating solid, flawless stone, a dull thud revealing a hidden fracture or a plane of weakness deep within. This was the highest form of material science, the strategic use of natural cleavage and fault lines. These masters were not fighting the mountain, they were reading its internal language. They understood that every rock formation has a grain, a natural tendency to split along specific planes created by immense geological pressures over millions of years. Their innovation was to find that grain and follow it. By identifying these natural separation planes, they could isolate colossal blocks with an almost surgical precision, using far less energy than if they tried to cut across the stone's internal structure. At sites like the ancient Egyptian quarry at Aswan, the evidence is still written on the walls. The massive cavities left behind are not random pits. They follow distinct linear paths that align perfectly with the natural bedding planes in the granite. The builders did not just randomly hack at the stone, they worked with its inherent weaknesses, turning geological flaws into architectural advantages. How was this deep, almost intuitive geological knowledge passed down through generations without a single textbook or formal school? It was a living curriculum taught on the quarry floor. An experienced master would point out a hairline crack to his apprentice, showing how it ran deep into the bedrock and could be exploited with a few carefully placed wedges. They shared a language of stone where every color variation, every subtle ridge, told a story about what lay beneath. This intimate understanding of local geology was a fundamental innovation in resource management, transforming an entire landscape into a predictable, manageable source of perfect building material. It was a partnership with the earth itself, a dialogue that began with a single, knowing tap. While the abrasive slurry did the heavy cutting, the final details demanded something more refined. A master carver's hand needed a tool that could hold a razor-sharp edge, something that could define the delicate curve of a lip or the intricate feather on a hieroglyphic bird without bending or wearing down after a few strokes. The soft copper chisels used for rough work were useless here. This challenge sparked a parallel revolution not in stone but in fire and metal. Ancient metallurgists began to experiment, moving beyond pure copper. They discovered that by adding small, carefully measured amounts of arsenic or tin to the molten metal, they could fundamentally transform its nature. The resulting bronze was a different class of material altogether, harder and far more resilient. An arsenical bronze chisel, for instance, could maintain its working edge significantly longer against the relentless abrasion of granite dust. This was not about creating a tool harder than the stone, but one durable enough to effectively guide the abrasive process and execute fine work without constant resharpening. The innovation was in the specific formulation. These were not general-purpose alloys, but specialized recipes likely developed for and guarded by guilds of stonemasons. What smelting techniques allowed them to consistently introduce these elements, often toxic like arsenic, into the mix without catastrophic failure? It required a deep, experiential knowledge of temperatures and fluxes, a chemistry practiced at the forge. Archaeological evidence, such as unusual metal residues in crucibles and the analysis of tool fragments from advanced workshops, hints at this deliberate, task-oriented metallurgy. A slightly harder, more wear-resistant bronze point would have been revolutionary for detailed inscription work. It allowed the artisan to apply greater pressure with confidence, to create cleaner, deeper lines, and to bring a new level of artistry to the most unforgiving materials. This evolution of the tool itself represents a critical partnership where the advancement of metalworking walked hand in hand with the ambition of the stoneworker, together pushing the boundaries of what was possible to carve into eternity. A subtle, almost invisible transformation could take place within the stone itself. Certain types of siliceous rock, when heated to a precise, carefully controlled temperature, underwent a fundamental change in their very nature. The bonds between their crystalline particles would shift, the internal stresses relaxing just enough to make the stone far less resistant to a chisel or abrasive. This was not the violent thermal shock of fire setting, but a gentle, calculated persuasion of the material's soul. The innovation was in the control. Ancient technologists were not just applying heat, they were regulating it, holding the stone at a specific thermal threshold to achieve a desired molecular effect. Once the stone cooled, it would regain much of its original hardness, but during that critical window of workability, it could be shaped with significantly less effort. This process mirrors the principles of modern material science, where heat treatment is used to temper steel or strengthen ceramics. The discovery of this technique would have required generations of meticulous observation. How did they determine that one type of stone responded to a gentle, sustained heat from a charcoal bed, while another required a more intense, direct flame? It speaks to a deep experimental tradition. A slow accumulation of data points where success and failure were recorded not in writing, but in the memory of the artisans and the quality of the finished work. The evidence is subtle, perhaps visible in the microscopic analysis of tool marks on certain artifacts, where the ease of cutting suggests a stone that was more cooperative than its natural state should allow. This represents a pinnacle of material understanding, moving beyond the stone's surface to manipulate its hidden architecture. They were not merely carving rock, they were temporarily reprogramming it, a silent collaboration between fire and crystal that yielded masterpieces from the most stubborn of mediums. A master blueprint for a stone block existed not on papyrus, but in the mind of the architect, translated into reality through an intricate language of knots and geometry. The true foundation of precision was a simple yet revolutionary tool, the standardized measuring cord. These cords, knotted at precise intervals, were the ancient world's living tape measures, their lengths verified against a master standard to ensure that every team, from quarry to final placement, was working to the same exact scale. This created a universal language of dimension across vast distances and generations of workers. The innovation was the system itself, a network of shared information that guaranteed consistency. How could a team carving a stone in a quarry miles away create a block that would fit perfectly into a waiting space in a temple wall? They were all using cords knotted from the same fundamental unit of length. This eliminated the cumulative error that would have rendered complex, interlocking stonework impossible. The evidence is etched into the stones themselves. At sites like the Coricancha in Cuzco, Peru, the masonry features blocks with multiple interlocking angles and protrusions that fit together with breathtaking accuracy. This was not achieved by randomly shaping stones until they fit, but by precisely crafting each one to a predetermined, shared template before it was ever moved. The intellectual framework behind this was a sophisticated understanding of applied geometry. Builders used simple tools like set squares and plumb bobs to establish perfect right angles and vertical lines, and they employed geometric principles to lay out complex curves and arches. The development of the circle and its division into 360 degrees was not just an abstract mathematical exercise. It was a practical tool for orienting entire cities and aligning monuments to celestial events. This knowledge transformed a chaotic pile of individual stones into a single, coherent structure. The creation of a precise ashlar block was a multi-step ritual of measurement and verification, a dance of chords and markers that ensured every surface was true. This system of dimensional control was the invisible architecture holding the physical one together, proving that the greatest innovation was not in the stonecutter's hand, but in the universal measure he held. An ancient arch does not simply hold weight, it conducts a silent symphony of force. The master builders understood that stone, for all its apparent solidity, is a dynamic medium that must be guided rather than commanded. Their most profound innovation was designing entire structures as unified systems, where every block was shaped to channel immense loads along efficient, shared pathways, preventing any single point from bearing a destructive concentration of stress. This was the science of stress distribution, an intuitive grasp of physics that turned piles of rock into eternal monuments. Consider the corbelled arch, a staircase of stone that seems to defy gravity. Each projecting block is counterbalanced by the weight of the masonry above it, creating a stable, inward-leaning structure that transfers the load downward along a graceful, calculated curve. This is not a random stack, it is a meticulously engineered chain where every link supports the next. The same principle is visible in the cantilevered galleries of Asian temples, where massive beams extend far beyond their supports, their own weight perfectly balanced to create soaring, open spaces below. The innovation was in the foresight. These builders were not just assembling stones for the present moment, they were modeling how forces would interact and settle over centuries. They understood that a perfectly fitted joint does more than keep out the weather. It turns two separate blocks into a single, stronger unit that distributes impact and seismic shock across a wider area. How did they test these designs without complex mathematics? Their laboratory was one of scale models and incremental observation. They likely built small, full-scale mock-ups in quarries to observe how their shapes behaved under load, learning from minor collapses to perfect the final, monumental version. This systemic thinking is what separates simple piles of rock from the seamless walls of Sacsayhuaman or the enduring vaults of Mycenaean tombs. Each stone was not just a piece of the puzzle, it was an active participant in a structural collaboration, a frozen dialogue of push and pull that has remained in perfect equilibrium for thousands of years. That final, perfect polish was not the only place where ancient science turned liquid into a tool. The tremendous friction generated by dragging a multi-ton block or spinning a copper drill bit created a fierce enemy, heat. This heat could warp wooden sledges, prematurely dull metal tools, and even fuse an abrasive slurry into a useless, glassy paste. The solution was an innovation as slippery as it was brilliant, the development of specialized lubricants. Animal fats rendered from cattle or sheep and oils pressed from plants like olives or castor beans became an invisible but essential component of the stoneworking arsenal. These natural substances were more than just simple greases. They were early tribological fluids, carefully selected for their ability to reduce friction and manage thermal energy. A worker pouring oil into a deepening drill cut was not just making the work easier, he was actively cooling the tool and the stone, preventing the destructive heat buildup that could stall the entire operation. The lubricant created a protective boundary layer, allowing the abrasive quartz particles to roll and cut freely rather than getting stuck and polished smooth against the granite. This dramatically increased the efficiency of sawing and drilling, extending the life of valuable copper tools and making the precise shaping of hard stone a sustainable, repeatable process. How did they discover which plants yielded the most slippery oils, or which animal fats provided the longest-lasting film under pressure? This knowledge would have been born from 1,000 small observations, from watching how certain seeds felt when crushed, or noting how a particular grease made a heavy door pivot more smoothly. The right lubricant could mean the difference between a team of 50 and a team of 200 men being needed to move a single obelisk. By reducing the coefficient of friction, these substances effectively multiplied human and animal power, turning impossibly heavy loads into manageable challenges. While these organic compounds have long since vanished from the archaeological record, their necessity is written in the sheer scale of the achievements themselves. The creation of specialized lubricants represents a profound understanding of an invisible force, a quiet mastery that allowed the great stones to glide into their eternal places. The quarry floor was a landscape of calculated order, not chaotic excavation. Each cut into the granite was a deliberate move in a long-term strategy, a testament to an innovation that went beyond engineering and into the realm of resource economics. Ancient quarry masters did not simply attack the rock face, they engaged with it in a planned sequence, carefully extracting blocks in an order that minimized waste and preserved the structural integrity of the quarry wall itself. This was selective quarrying, a sophisticated form of material conservation that viewed every piece of stone, large or small, as a valuable asset. The largest, most flawless blocks were destined for grand statues or monolithic pillars. But the smaller pieces, the offcuts and fragments that a less thoughtful operation would have left as rubble, were carefully collected and set aside. These became paving stones, fill material for cores of walls, or raw material for smaller artifacts and tools. This efficient mindset is written into the archaeological record of ancient quarries, where the patterns of extraction show a logical progression, and the debris piles are surprisingly small relative to the colossal structures they supplied. What organizational systems ensured this careful stewardship across generations of workers? It required a master plan, a vision for the entire life cycle of the quarry site that balanced immediate needs with future supply. This approach demonstrates a form of sustainable resource use that we often consider a modern invention. They were not just builders, they were the original practitioners of a circular economy, maximizing the yield from every single site and ensuring that nothing was wasted. This conservation philosophy required an intimate knowledge of the stone's quality and consistency throughout the entire quarry, allowing planners to match the right material to the right purpose long before the first cut was made. The true innovation was seeing the mountain not as an infinite resource to be plundered, but as a finite, precious library of building material where every volume had its designated place. The final act of the master builder was to shield their creation from time itself. After countless hours of shaping and polishing, the stone was at its most vulnerable, its pristine surface exposed to a relentless assault from sun, rain, and wind. The innovation was to coat the finished work in a protective skin, a barrier crafted from the very bounty of nature. Artisans would have heated mixtures of beeswax, tree resins like pine pitch, or plant oils, creating a thick, viscous liquid that could be carefully brushed or poured over the stone. As this substance cooled and hardened, it sealed the microscopic pores of the granite or limestone, preventing water from seeping in, freezing, and causing the surface to spoil and crack over the seasons. This was more than a final touch. It was a profound shift in perspective, moving from the immediate triumph of construction to the far-sighted responsibility of preservation. The development of these treatments represents the completion of the stoneworking cycle, an understanding that true mastery meant ensuring a monument would endure for generations, not just stand for a moment. What natural laboratories led to these discoveries? Observation would have shown that a beeswax seal preserved food, or that pine resin hardened into a durable, waterproof shell on a wounded tree. Applying this same logic to stone was a stroke of genius. While most of these organic layers have long since weathered away, subtle clues remain. Some classical marble statues, for instance, retain traces of pigments that were likely mixed with a resinous binder, a combination of art and preservation. On certain Egyptian obelisks, researchers have detected faint chemical residues suggesting a surface treatment that would have originally given the stone a deep, lustrous sheen while protecting it from the desert sands. This knowledge transformed a static object into a maintained legacy. The application of a protective coating was a ceremonial act, a final blessing that entrusted the stone to the future, a quiet promise from the ancient world that their work was built to last. The true genius of ancient engineering reveals itself not in any single tool, but in the seamless choreography of many. A grand temple did not rise from the application of one technique, but from a masterfully sequenced production line where each specialized method played its part at the perfect moment. The entire process began with fire setting at the quarry face, where the strategic application of heat and water isolated colossal blocks from the living rock with a force no tool could match. Once transported to the workshop, the same block would be shaped by teams using dolerite pounders and abrasive-laden saws, transforming the rough-hewn stone into a precise geometric form. Then the drillers would take over, their hollow tubes spinning with abrasive slurry to create the mortises and sockets for perfect joinery. Finally, the surface would pass to the polishers, who used progressively finer pastes to erase all traces of the work and bring forth the stone's inner light. This was an integrated manufacturing system, a proto-industrial pipeline operating millennia before the Industrial Revolution. The innovation was the systemic vision that saw how these disparate technologies could interlock. How was such a complex workflow managed across hundreds of workers without written schedules or digital communication? It required a hierarchy of master craftsmen, each an expert in their domain, who shared a common architectural language and a unified goal. Knowledge was the most critical tool, transferred through demonstration and oral tradition, ensuring that the quarryman understood the needs of the driller and the driller the requirements of the polisher. This coordination allowed for a division of labor so effective that it could tackle projects of staggering complexity, from the multi-ton pillars of Karnak to the interlocking walls of Machu Picchu. The synthesis of these methods represents the pinnacle of applied ancient science, a holistic understanding that the whole was infinitely greater than the sum of its parts. A master craftsman's deepest secret was not the recipe for an abrasive slurry, but the living apprentice who memorized his every move. The most resilient innovation was not a tool of stone or metal, but the sophisticated social machinery for passing knowledge from one generation to the next. This cultural transmission created invisible bridges of technique that spanned continents and centuries, allowing the precise art of hard stone working to become a repeatable, standardized science. In workshops from ancient Egypt to the Andes, the primary classroom was the worksite itself. A young apprentice would spend years observing, fetching materials, and performing simple tasks, his eyes absorbing the master's rhythmic hammer strokes, the exact angle for a drill, and the subtle sound that signaled a perfect cut. This was an education built on muscle memory and oral tradition, where complex procedures were encoded in stories, songs, and ritual practices. Technical knowledge was not written in manuals, but performed in a daily dance of demonstration and imitation, ensuring that hard-won expertise was not lost to time. The evidence for this standardized learning is written in the stone itself. How else can we explain the nearly identical use of the wedge and feather technique for splitting granite in both Inca and Pharaonic quarries, two cultures separated by an ocean? The consistent angles of drill holes found in artifacts from disparate regions point to a shared, deeply ingrained understanding of effective practice. This suggests either a remarkable case of independent discovery solving the same physical problems, or the faint, far-reaching echoes of knowledge networks we have yet to fully map. Guilds and craft families acted as the guardians of this specialized information, treating it as a valuable inheritance. They developed their own lexicons and teaching methods, creating a closed loop that preserved quality and control. The innovation was this self-perpetuating educational structure, a social technology that turned individual cleverness into enduring cultural capability. The true monument was not just the finished temple, but the unbroken chain of hands and minds that built it, a legacy of learning carved not in stone, but in the very fabric of human ingenuity. The true test of an ancient builder's genius was not a single quarry, but 1,000 different landscapes. They carried a mental toolkit of principles, not rigid rules, allowing them to adapt to whatever stone lay beneath their feet. This was innovation as a living process, a dynamic conversation with the local earth. A technique perfected on the fine-grained limestone of Egypt would fail miserably against the vesicular, pockmarked basalt of Mesoamerica. So, the builders observed, they learned that volcanic tuff, though relatively soft, was full of trapped gases that made it crumble under a pounding stone. The solution was to use lighter, more precise tools and to work the material when it was slightly damp to reduce dust and control fracturing. This location-specific tailoring is why the stonework of Easter Island, with its compressed volcanic ash, looks so distinct from the granite marvels of India. Each region developed its own signature style, a direct reflection of its geology. When a civilization expanded into new territories, its engineers faced an immediate and practical challenge. How do you build a lasting monument with a stone you have never worked before? The process would begin with small-scale tests, much like a modern geologist's field assessment. They would strike samples to judge their fracture patterns, test different abrasives to see which grit worked best, and even attempt to drill or carve small sections to understand the stone's internal consistency. This rapid, on-the-ground research and development was the engine of their technological spread. It was not a one-size-fits-all imperialism of technique, but a flexible, intelligent adaptation that respected the character of the local material. This ability to listen to the stone itself, to let its properties dictate the methods of its shaping, represents the highest form of practical wisdom. Their greatest innovation was a mindset of perpetual learning, ensuring that their art could take root anywhere on Earth. The rhythm of the stonecutter's hammer was more than a sound of labor, it was a form of prayer. In many ancient societies, the process of shaping hard stone was deeply intertwined with spiritual beliefs, transforming a technical craft into a sacred ritual. This was not a separation of science and spirit, but a powerful fusion where cosmology directly guided the hands of the artisan. The very selection of a stone was often a symbolic act, with certain types of rock chosen not just for their physical properties, but for their perceived connection to deities, ancestors, or celestial forces. A particular granite might be quarried from a mountain considered the home of a god, making the stone itself a fragment of the divine. This spiritual significance demanded a higher standard of care and precision, an attitude that naturally fostered technical excellence. Tools were not merely objects, they were consecrated. Before a critical cut was made, a chisel or drill might be anointed with oils or blessed with incantations, a practice that served a dual purpose. While honoring the spiritual nature of the work, this ritualistic preparation also forced the craftsman to pause and focus, to mentally review the steps ahead, reducing the chance of a careless error that could ruin a sacred object. The innovation here was not a new tool, but a mindset where the drive for perfection was fueled by a profound reverence for the material and its purpose. This cosmological framework sometimes pushed engineering in directions that pure utility might never have considered. The most striking example is the precise alignment of monuments with celestial events. The desire to capture the first ray of the rising sun on a specific day, or to have a corridor point directly to a certain star, required an architectural precision of the highest order. This symbolic goal, rooted in a belief system, demanded and therefore drove the development of advanced surveying techniques, sophisticated geometry, and incredibly accurate stone shaping to achieve that perfect alignment. How did the spiritual belief that a stone possessed a life force influence the way it was worked? It likely encouraged more patient, controlled methods like abrasion and drilling, which could be seen as persuading the stone rather than brutalizing it. The rhythmic, repetitive nature of many rituals also acted as a powerful mnemonic device, preserving complex technical sequences through song, dance, and ceremonial reenactment. The knowledge of how to dress a drill or mix an abrasive slurry was embedded within a story about a god or a hero, ensuring it was passed down faithfully through generations. This intersection of technology and belief created unique pathways to discovery, where the quest for symbolic meaning became a powerful engine for practical innovation. The calendar itself was a tool as vital as any chisel or drill. Ancient builders did not simply work on stone, they worked within the world's natural rhythms, synchronizing their construction schedules with the turning of the seasons. This was an innovation of timing, a sophisticated orchestration where quarrying and shaping were scheduled to align with environmental conditions that actively aided the work. During the wet season, when rains filled gullies and streams ran high, the focus would shift to the quarries. This was the time for the heavy, water-intensive work of fire setting and abrasive sawing, when an abundance of water meant a constant, efficient supply for creating the abrasive slurries essential for cutting hard stone. When the dry season arrived with its stable air and predictable, firm ground, the work transitioned to the final shaping, precise measurement, and assembly on the building site. Dry conditions were crucial for the delicate work of laying out perfect angles and ensuring that measuring cords did not stretch or shrink with humidity, guaranteeing that every block would fit with breathtaking accuracy. This temporal planning required a deep, long-term vision. How did a project manager coordinate hundreds of workers, knowing that a specific phase of carving had to be completed before the rain ceased and the water supply diminished? It demanded a master calendar, one that blended astronomical observation with practical knowledge of local weather patterns. Evidence from ancient sites sometimes reveals these seasonal pulses in the archaeological record, with different tool marks and waste materials corresponding to wet season versus dry season activities. This was ecological engineering in its purest form, an understanding that the greatest efficiency came not from conquering nature, but from moving in harmony with its cycles. By listening to the environment, they turned potential obstacles like seasonal floods into powerful allies, ensuring that every drop of rain and every day of sun was put to its most effective use in the service of eternity. This journey through 26 material science innovations reveals a truth far more profound than any single technique. We are not looking at the work of primitive laborers, but at the legacy of brilliant engineers who saw stone not as an enemy to be conquered, but as a partner in a grand creative dialogue. Their solutions, from the microscopic grinding of abrasives to the immense leverage of fire and water, form a complete intellectual system. They understood the hidden physics within a rock's crystalline structure, the chemistry of a plant's sap, and the geometry of perfect force distribution. This practical knowledge, accumulated over generations and tested on a monumental scale, completely upends our modern assumptions about what ancient societies could achieve. The real wonder is not the silent, unmoving stone itself, but the vibrant, thinking minds that knew how to persuade it into form. They left behind a testament to human ingenuity that whispers a powerful message across the centuries. Our own world is filled with what we call impossible challenges, from material limitations to energy needs. Yet the legacy of these ancient builders asks us a simple, profound question. If they could reshape the very bones of the earth with patience, observation, and creative thinking, what could we accomplish if we applied the same relentless ingenuity to the puzzles of our time? The stones stand as a permanent reminder that when knowledge and determination converge, human potential is truly without limits.